K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on chemistry of environment. We are discussing about fundamental aspects of chemistry relevant to environmental studies. Earlier class, we discussed about thermodynamics and kinetics aspects. And today, we are going to look at another important fundamental aspects, namely chemical equilibrium. Because all this waste and its treatment, everything about chemicals, and ultimately it has to come to equilibrium. Okay. So, let us see what is this. And usually chemical equilibrium may be defined as a state of a reversible reaction when the two opposing reactions occur at the same rate and the concentration of the reactants and products do not change with the time. So, this is a definition for a particular chemical equilibrium based reaction, in which the forward reaction and backward reaction will be at the same time. That is a reversible and irreversible reactions thing. And a true equilibrium of a reaction can be attained from both the sides, that is from the reactant side as well as from the product side. It is possible to attain the true equilibrium in a particular chemical reactions. In this chemical equilibrium, both reversible and irreversible reactions can be dealt with. So, a reaction which can go in the forward and backward reaction simultaneously under the same condition is usually called reversible reaction, and this is very important for chemical equilibrium aspects. Okay. Let us consider a general reaction. A and B reacts to form the products C and D, and this is a forward reaction. That is, the two reactants A and B react to form the products C and D, and this is a forward reaction rate constant. And same thing, the reversibility or the equilibrium which it deals with can be also attained from the reverse reaction. That is, the products C and D react to form the A and B. Here the A and B, I am sorry, C and D becomes reactants, the products become A and B, and this reaction is called reversible reaction. So, that is what the Kr denotes rate constant for the reversible reaction. So, this particular reaction is in equilibrium and it is reversible, that is A and B reacts to form C and D. This is a forward reaction. If you put it in the backward side, it is a reaction. And in these type of reversible equilibrium based reaction, when the rate is 0, net concentration of A, B, C and D are in equilibrium with each other. When the rate of the reaction is 0, that means no conversion of reactant to product or products into reactant is not taking place, and that is what it refers to chemical equilibrium. And it can be determined with respect to the rate as well as amount with respect to the reactant and products formed with respect to time. And if you see the rate of any reactions, and the forward reaction rate will go on decreasing, because for the simple reason the initial concentration is to start with the reaction, it was high. The moment some reactants are converted into reactants, what happens is the rate of the reaction slowly decreasing. That is what indicates here, the reactant concentration is decreasing and the product concentration goes on increasing. At one point of time, both the concentration of the reactants and products will be the equilibrium. There is no change in amounts of this product and reactant concentration. So, such condition is known as equilibrium condition. So, this can be expressed with respect to amount of the reactant products or the rate with respect to the forward rate reaction and reverse rate reaction. To start with, the rate if you express, the forward rate goes on decreasing, whereas the reverse rate goes on increasing, and at equilibrium the rate of the forward and reverse reaction will be equal. That means, at that condition no change in concentration of reactants as well as products in the particular reaction. And this is what for a general reaction X reacts to form the product Y, we can write this, the change in concentration of the X with respect to time A, or also with respect to product formed also, as I mentioned before, can be written here. It is positive sign because products are formed increasing with respect to time, whereas here X it is decreasing, that is why the minus sign. And we will see some of the characteristics of a chemical reaction at equilibrium condition. It has some special peculiar characteristics. As I mentioned before, constancy of concentration. At equilibrium, the constancy of concentration of both reactants and products will be there. So, when a chemical equilibrium is established, especially in a closed vessel at constant temperature, the concentration of various species like reactants and products formed in the chemical reaction remain unchanged. This is one of the important thing. At equilibrium they will remain constant, and the reaction mixture consisting of reactant and products at equilibrium is called equilibrium mixture, okay, and which both reactants as well as products will be there and they will be at equilibrium, and because of this reason it is known as equilibrium mixture. The concentration of reactants and products at equilibrium are called as equilibrium concentration of the reactant and products, whatever it takes part in a particular chemical reaction. And equilibrium can be initiated from either side, that is a forward side or backward side, and the state of equilibrium of a reversible reaction can be arrived at whether we start from reactant or products. For example, you just consider the reaction, that is hydrogen gas react with iodine to form hydrogen iodide, can be achieved whether we start with hydrogen and iodine or with starting with the HI, hydrogen iodide. Generally, equilibrium cannot be attained in an open vessel. In an open vessel it is exposed to the outside one, and definitely it is very difficult to achieve equilibrium. So, open vessel very difficult, always the equilibrium can be attained with in a closed vessel only. The other characteristics of chemical equilibrium are catalyst role in equilibrium. Catalyst does not alter the equilibrium. Even in reaction of two reactants, we add catalyst to speed up the reaction. Definitely catalyst does not alter the equilibrium in a reaction, and when a catalyst added to the equilibrium system, it speed up the rate of the both forward as well as reverse reaction to an equal extent. That is the role of the catalyst. Therefore, the equilibrium is not changed, but the state of equilibrium is attained earlier by lowering the activation energy. The catalyst, as shown here, it lowers the activation energy and brings out attaining the equilibrium quickly. That is, hasten the process in a different way by lowering the activation energy in presence of catalyst, and catalyst helps to achieve the equilibrium faster. And the value of equilibrium constant does not depend on the initial concentration of the reactants. The equilibrium constant value does not depend on the initial concentration of the reactants. At equilibrium, the free energy change is minimum. This is again at equilibrium condition, the thermodynamic parameters free energy normally represented by G value is minimum for a particular reaction. If it is a irreversible reaction, usually it is delta G value, free energy change is negative for a spontaneous reaction. For equilibrium reaction, the free energy change is minimum or 0. Temperature is another important thing which is playing a crucial role in equilibrium. When temperature is changed, the forward and backward reaction rate are changed, and the equilibrium concentration of reactants and products are also changed if we alter the temperature. And the principal effect of the temperature and the equilibrium is in changing the equilibrium constant value. The K value, capital K normally represented, is altered by changing the temperature. So, the equilibrium constant is constant only if the temperature remain constant. If you change the temperature, then the equilibrium constant value also will change. Increasing the temperature will shift the equilibrium in the direction of endothermic reaction, and decreasing the temperature will cause a shift in the direction of exothermic reaction. So, depending on whether a particular chemical reaction is endothermic or exothermic, we have to alter the temperature, either decrease or increasing to attain chemical equilibrium faster rate. Suppose we apply heat in opposite direction, it will not achieve equilibrium and difficulty will be there. And chemical equilibrium is governed by law of mass action, and it is stated that the rate of a chemical reaction is proportional to the active masses of concentration. This is the law of mass action which governs with chemical equilibrium. The rate of a particular chemical reaction is proportional to the active masses of reactants. So, by the term active mass in chemical equations, it means that the molar concentration, that is the number of moles per liter in which they actively take part in a particular chemical reaction. By considering a general chemical reaction, we can arrive at a equilibrium constant value. Just consider again in the general reaction, two reactants, namely A and B, reacts to form the products C and D. The appropriate mole numbers are given as the small a, b, c, d. And as per the law of mass action, just now I told you, the rate of the forward reaction given by rate of the reaction is equivalent to K forward reaction, that is a rate constant for this, and depends on the rate of the active mass concentration raised to the power number of moles. Similarly, both the reactants A and B, and the rate for the reverse reaction, this reaction in this direction, if you write, the rate of the reverse reaction is equivalent to K R into active mass of C and D raised to the respective number of moles of C and D. Here the Kf and K are the rate constant for the forward and reverse reaction for this particular general reaction. At equilibrium, we have seen the rate is forward as well as backward reaction or reverse reaction will be the same. So, we can bring this above the value like this, and this can be rewritten like this by bringing the K values one side and the active mass concentration of the particular reaction the other side, and it will be reduced to this value, that is Kf divided by Kr, that is equivalent to Kc. This is called equilibrium constant. Capital K is normally represented by equilibrium constant and small k rate constant. So, for the above general equation, the equilibrium constant is equivalent to active mass of product C and D divided by active mass of reactants A and B raised to the power of number of moles whatever it takes up in the particular reaction. So, this is very important Kc value. And suppose the reaction involves gaseous reactions, gaseous reactants. Okay. Partial pressure of this instead of concentration, partial pressure of the gaseous reactants are very important, and they are related to the equilibrium partial constant is equivalent to Kc into RT delta Ng. Here all temperature T, gas constant, this is the equilibrium constant, and delta Ng is actually the total number of stoichiometric moles of gaseous product minus total number of stoichiometric moles of gaseous reactant in the particular general things. So, this way it can be governed by this partial pressure of this gaseous reaction. This is a general relationship, the Kp value and Kc value related to this, and delta Ng very importantly. Le Chatelier is one of the popular scientists. He studied about chemical equilibrium, and he has come out with a principle or a postulation for this. And he made a lot of research on this, and he found three main factors in a particular chemical reaction, namely concentration, temperature and pressure, especially for gaseous reaction, that alter the state of equilibrium. In a particular chemical reaction, if you change any one of this term, that is pressure or concentration of the reactants as well as temperature, then we can alter the state of the equilibrium. Addition of catalyst merely hasten the approach of the equilibrium, it will not alter, it helps in attaining the equilibrium faster, that is the role of the catalyst, but the temperature, pressure, concentration can alter the equilibrium. So, by this he has come out Le Chatelier principle, he has come out of the statement, that is, if a system at equilibrium is subject to a disturbance or a stress, then the equilibrium shifts in the direction that tends to nullify the effect of the disturbance or stress applied to the system. So, this is the Le Chatelier principle, that is, if a system at equilibrium is subject to a disturbance or a stress, then the equilibrium shifts in the direction that tends to nullify the effect of the disturbance or stress. And Le Chatelier principle indicates whether more reactants or more products will be made by applying any one of this term. So, this is in wastewater treatment very useful in pollutant removal methods. We have to closely study by altering any one of this thing, so that we can achieve the fast removal of this pollutants actually involved in a chemical reaction. And we have many type of reaction, especially in the environmental field, is very important. One such thing is acid base equilibrium, that is controlled by pH and water equilibrium, all aquatic system controlled by acid and base, and this is called water equilibrium, and pH has a big role to play. And not only this, even the buffer system, okay, are very important. Buffers also can be explained based on this chemical equilibrium, acid base equilibrium. That is very important. The Henderson equations are very popular. Then and there, these type of equilibrium there, and that will be dealt with this chemical equilibrium. I will explain little bit there. And similarly, there are other system which is also governed by chemical equilibrium concept in environmental field. One is solubility. The solubility of gases like carbon dioxide is also very important, and similarly solubility of sparingly soluble salts, especially toxic metal hydroxide, are very important. So, I will explain all these things whenever we are going to discuss these particular aspects. Similarly, redox reactions also involving iron 2 or iron 3 and other complex reactions like a chromium 3 or chromium 6, wherever there we will discuss this chemical redox reaction, that is also gone by equilibrium. Similarly, complex formations reactions also we will discuss then and there depending on the thing. The complex formation alteration, just I want to give a simple example which is a routine in environmental field. Normally the chloride estimation we will do by Morse method using silver nitrate as a reagent taking the burette. At the end of the reaction, that is titration, normally the flask, conical flask led to the curdy white precipitate of silver chloride. Okay. To change this, normally we add ammonia, because silver amine complex formation will take place. The insoluble silver chloride is converted into silver amine complex. So, like this we can shift the equilibrium of this. Similarly, any silver compounds, wherever it is a problem, the complex formation will help to remove the strain also. The chemical equilibrium is also subject to thermal condition or thermal equilibrium. Zeroth law of thermodynamics, which is again very important. If there are three systems A, B, C, if the two systems are in equilibrium, the third system is also in equilibrium in touch with any one of the system A or B, then all the three systems will be in equilibrium thermally. Okay. So, this is the basic principle of zeroth law of thermodynamics, in which thermal equilibrium is dealt with. So, like this, the chemical equilibrium is also very important. Whenever we have to shift or alter the equilibrium, we have to pay attention to our Le Chatelet principle, which will help in altering or shift the equilibrium, so that we can achieve the conversion of the pollutants normally faster. That is what ultimately the waste treatment or eliminating the particular pollutant is very important. That is why. But in chemical synthesis, in the manufacturing industries, they are interested in more conversion of product. So, depending on whether you have to play the temperature, that depends on whether it is a endothermal reaction or exothermal reaction. So, application of temperature or cooling may help in achieving the equilibrium faster, and that is what the school you might have studied all these things, the Haber process of ammonia synthesis from nitrogen and hydrogen. Okay. That is a direct application of Le Chatelet principle, most commonly used for preparing the ammonia process and ultimately to urea preparation. In the environmental studies, we discuss with a lot of equilibrium involved in, especially in the aquatic system, like acid base equilibrium in water, solubility equilibrium, chemical complex formation, redox reaction, all are important in environmental studies. And especially in the water, the equilibrium constant value is well known, KW value, it is 1 into 10 power minus 14 at 25 degrees Celsius. That is, the concentration of H plus ion and hydroxide ion, if you multiply, this will come to this equilibrium. This is called water equilibrium, and this equilibrium can be shifted or adjusted by adding acid or alkali. If you add more acid, the system will become, the H plus ion concentration will become more, and at the same time the hydroxide ion concentration will decrease in the aquatic system. So, like this it will adjust, and same time if you add alkali, again it will adjust the system value, the H plus ion will decrease, and this is very important. And environmental studies, we encounter lot of buffer solution. Okay. These buffers are very important to maintain the pH at a particular value. Okay. And for this value, similar to KW value, the pKa value of acids as well as pKb values of bases are very handy. Based on the weak acid and weak base, we encountered or we used lot of buffer solution to maintain the pH at equilibrium condition, and natural water also maintain the equilibrium value. The carbonate bicarbonate in water acts as a very good buffer. So, buffer is one of the thing which helps to maintain equilibrium. By the small addition of acid or alkali, the buffers will not alter the change the pH of the solution at a higher value. For the small addition of acid or alkali, the system will adjust itself. This is one especially in aquatic system. Similarly, other equilibrium with respect to solubility of gases and solids also very important, in which gases, for example, carbon dioxide dissolve in water to form carbonate, bicarbonate depending on the pH of the system. So, this will be in equilibrium, and acid medium or alkaline condition again, because carbon dioxide being a weak acid, depending on alkaline medium, the concentration of free carbon dioxide will be converted to either bicarbonate or carbonate. Similarly, solids in environmental field we encounter lot of solids, especially toxic metal ion removal by applying this solubility equilibrium, that is Ksp value of toxic metals, it is all removed either as a carbonate or sulphide or hydroxide is one of the thing. So, all these aspects I will explain in detail when you are going to discuss about the removal of heavy metals by carbonate or sulphide. There I will explain these aspects in more detail. Similarly, other reactions of redox reaction in aquatic chemistry is also very important, and we encounter a lot of metal ions like iron, arsenic, chromium, which all can exist in different oxidation state. For example, iron Fe2 plus and Fe3, arsenic plus 3 and plus 5, chromium plus 3 and plus 6. So, all these things depending on the environmental conditions, these metal ions may be changed from one form to another form, okay, so that the equilibrium will be altered. So, these aspects, redox reactions based one also we will see and discuss in detail at the appropriate section. Similarly, complex formation in aquatic system, that also be affected by are governed by chemical equilibrium and complex formation, with especially naturally occurring lot of humus material. Many metal ions forms complex with their OH group and COH group, and that is also affected or changed by altering the conditions of the medium. So, like this, the chemical equilibrium is governed by variety of processes and variety of reactions type. We have all these things, we can, if you want, we can shift the equilibrium. For example, the complex formation in environmental field, the students are very familiar with estimation of chloride in water by Morse method of titration, in which silver ion is used as a reagent. During the process titration, silver ion will react with the chloride in water, forming an insoluble Cardi white precipitate that will be deposited as a Cardi white precipitate to the conical flask in which we are going to do the titration. So, removing the silver chloride is very difficult. Now, suppose we add ammonia to the same solution, it will form complex silver ammonium complex, which is water soluble, that can be washed away from the flask very easily. So, this way we can change or shift the equilibrium also by the appropriate reagents. And similarly, another aspects as thermal equilibrium, zeroth law of thermodynamics, which deals with the thermal equilibrium. Actually, if you consider three systems A, B, C, and all the three are in contact, suppose A and C are in equilibrium, then A and B is also in equilibrium. Okay. So, any out of the three, any two are in touch with the same time thermally, or the temperature of A and C is same and A and B is also same, then the temperature of the B and C also will be the same. This is the zeroth law of thermodynamics, in which thermal equilibrium concept is explained. So, like this, in the environmental field also very important to deal with the chemical equilibrium, especially the exothermic reaction and endothermic reaction. The thermal things are very important, and application of heat or cooling will speed up the reaction products formation. One of the well known example is ammonia synthesis by Haber's process by reacting nitrogen and hydrogen and lowering the temperature or increasing the temperature will help in removing the products or get more products is very important. So, to sum up, chemical equilibrium, especially in conjunction with thermodynamics and chemical kinetics, very important to understand the environmental aspects of chemicals, which are all viewed as a pollutant, and we are all interested in removing the pollutants from the wastewater or Here also we are important to remove the pollutants, air pollutants, and we have to go for some kind of chemical based treatment or biological method, in which they are also governed by equilibrium if it is a reversible reaction. So, we have to pay attention to these aspects, which parameters govern the process, how we can alter the equilibrium by applying either thermal heat or other reagents concentration. By altering the reaction things, we can very well shift the equilibrium in our favor to get more product. If it is a chemical synthesis, that is their interest, whereas in the environmental field we want to eliminate the pollutant by appropriate chemical reaction. So, we have to see which parameter is crucial in combination with thermokinetic parameters, the equilibrium can be altered the favorable way. Thank you very much.